Now we return to the theorem that we want to prove, which is stated here. So we considered a bounded subset of R, and the statement of this theorem says that E, this bounded subset E, is Jordan measurable if and only if the indicator function for this set E, chi E, is Riemann integrable, in the sense that this integral exists. And here I have added another statement which then identifies the Jordan measure with this integral from a to b of chi E dx. So not only that Jordan measurability of E implies the Riemann integrability of the indicator function and vice versa, but the Jordan measure is actually exactly the integral, the value of the integral of the indicator function. So let's see a proof here, and we will in fact show that the inner Jordan measure of E is precisely equal to the lower Darboux integral of chi E, and the outer Jordan measure of E is precisely the upper Darboux integral of chi E. So I will just prove the statement for the inner Jordan measure, and the proof for the outer Jordan measure is very similar, so I will leave that as an exercise. So first let's show that given epsilon greater than 0, the inner Jordan measure of E is less than or equal to the lower Darboux integral plus epsilon. So since epsilon is arbitrary, then it would imply that the inner Jordan measure is less than or equal to the lower Darboux integral. So to show this, choose an elementary set A of E such that the inner Jordan measure is less than or equal to m of A plus epsilon. Now if E is a subset of this interval AB, then we can partition this interval AB as follows. So first choose intervals. You can in fact choose disjoint intervals ik such that A is the union of ik, k equal to 1 to n, let's say, and we can let j l from 1 to m be an arbitrary partition of the set AB minus A. So we take the partition inside A with the disjoint intervals ik, which is used in the disjoint union expression for the elementary set A, and we can take an arbitrary partition for AB minus A. Then the indicator function of A is a piecewise constant function such that chi A equals 1 on each ik and chi A equals 0 on each JL. So this is straightforward from the definition of the indicator function, because if a point x belongs to one of these ik's, then it belongs to A and we will have the value 1, and if it is outside A, then we will have the value 0. So this is still a piecewise constant function, and chi of A is less than or equal to chi of E. We have a pointwise inequality of functions. Chi A is less than or equal to chi E. So therefore M of A, which is by definition the sum of mik, k equal to 1 to n, this can be written as k equal to 1 to n 1 times mik plus L equal to 1 to m 0 times m JL. So this is the piecewise constant integral, Riemann-Darboux integral for the indicator function of E, which is the piecewise constant function. So we have identified that the piecewise constant Darboux integral, Riemann-Darboux integral for chi A is nothing but the elementary measure of the elementary set A. So therefore this is M of A is less than or equal to the lower Darboux integral from A to B of chi E x dx, since we also have that chi A x is less than or equal to chi E x for all x in this interval AB. So we have that the inner Jordan measure of E, which was less than or equal to MA plus epsilon, this is less than or equal to again the lower Darboux integral plus epsilon, and since epsilon is arbitrary, this implies that the inner Jordan measure is less than or equal to the lower Darboux integral of chi E. Now we have to prove the reverse inequality to show that the lower Darboux integral is less than or equal to the inner Jordan measure of E. So to show this, remember that by definition we had, this is the supremum of piecewise constant functions G, which are pointwise less than or equal to f, and you take the piecewise constant Riemann-Darboux integral for the function gx. Now what we can do here is the following. So if jk, so here I am using the fact that if given g a piecewise constant function such that g is less than or equal to so this is supremum over chi g less than or equal to chi E. If you take any piecewise constant function g such that g is less than or equal to chi E, because g is piecewise constant, we can choose a partition ik, k equal to 1 to n, again say of this interval AB such that g is equal to ck on, g takes the value ck on ik, and in fact the piecewise constant Riemann-Darboux integral for g is then ck m ik, k equal to 1 to n. Now in this sum, we note that each ck must be less than or equal to 1, since g is less than or equal to chi e, and the indicator function takes the value at most 1. So each ck is less than or equal to 1. Also, some of these ck's may be negative. So some of the ck's may be negative. So I will only consider those ck's which are positive in this sum and then bound it above by 1. So therefore, if ck is positive, so let me write the set of indices. If j prime is the set of indices, or let us say I prime is the set of indices in 1 to up to n, such that c I prime is greater than 0 for all I prime in this set I prime, which means that we are only choosing those indices for which this constant value for g is positive. So then the Riemann Darboux integral of gx, which is equal to the sum k equal to 1 to n ck measure of ik, this is then less than or equal to the sum over I prime m of I prime. So we are only taking those indices for which ci prime is greater than 0, but we already know that ci prime must be bounded above by 1, and since we have discarded the negative values, this can be bounded above, this sum ck mik can be bounded above by this new sum over the indices for which these values ck are positive, strictly positive. So now therefore the elementary set, the union I prime belongs to the capital I prime. This is an elementary set that sits inside E, that must sit inside E because ci prime is greater than 0, and therefore, so this is because since ci prime is greater than 0 for all I prime in I prime, because otherwise this pointwise inequality that we had for g and chi will not hold. So we have produced an elementary set which sits inside E, and the Riemann Darboux integral of g is bounded above by the elementary measure. This is the elementary measure of the union I prime of I prime. So this is our required elementary set that we needed, which sits inside E, and so we can write that the piecewise constant Riemann Darboux integral for g is less than or equal to the measure of the elementary set, which is the union of I primes over I prime, and this is less than or equal to the inner measure by the definition of the inner Jordan measure. So for each g, for any g in fact which is piecewise constant on AB, we have this inequality which bounds the Riemann Darboux integral of the piecewise constant function g by the inner Jordan measure of E. Now the right hand side of this inequality, this is independent of G. So therefore we can take the supremum over G less than or equal to chi e, G piecewise constant, and take the values of the Riemann-Darboux integral of these piecewise constant functions, and this supremum will also be bounded above by the inner Jordan measure of E, and this is nothing but, on the left hand side, this is nothing but by the definition of the lower Darboux integral. This is the lower Darboux integral of chi E. So we have the reverse inequality that we wanted. Now we come to the generalization of the previous result to any RD. We have seen it for dimension 1, and we can easily generalize these results to arbitrary dimension. So for that, if f is a function from a box in RD, so this is a box, this is a box, closed box in RD, let's say, and it's supposed to be bounded, is a bounded function, then one can define the upper and lower Darboux integrals, upper and lower Darboux integrals in the same way as before, replacing intervals with boxes in RD. So for example, the lower Darboux integral over this box B of this function fx is equal to the supremum of over functions g which are pointwise bounded by f, g piecewise constant, and one can take the we can take the piecewise constant Riemann-Darboux integral of this piecewise constant function gx over this box B. So here piecewise constant function means piecewise constant function g on B is the same as saying that there exists a partition of B into boxes bi I equal to 1 to n, such that G takes the value Ci on each G takes the value Ci on Bi, so it is constant on each Bi. So we have replaced intervals with boxes, and the rest of the definition remains the same, and in this case the piecewise constant Riemann-Darboux integral is by definition the sum Ci m of Bi I equal to 1 to n. So we can also define in the same way the upper Darboux integral. So this is the lower Darboux integral, and we can also define the upper Darboux integral of fx over this box B, which is the infimum of f less than or equal to h piecewise constant on B, and you can take the piecewise constant Riemann-Darboux integral of the function h. So with these notions we can write the theorem, which is a generalization of the previous theorem for arbitrary dimensions. If E is a subset, is a bounded subset of RD, then E is Jordan measurable if and only if chi E is Riemann-Darboux integrable, which is the same as saying that if E is sitting inside a box B, then the Riemann-Darboux integral of chi E x dx over this box B exists. And in this case, the Jordan measure of E is precisely this integral of the indicator function over B. So this is the straightforward generalization using the same proof. Basically, we can rewrite the proof for arbitrary dimensions and it will work fine. So as a corollary, as an application of this theorem or a corollary, we state the following result, that if f is a function, is a bounded function over an interval AB, then f is Riemann-Darboux integrable if and only if the subset EF of R2 given by, this is similar to the region under the graph, actually exactly the region under the graph which we have seen before, such that x belongs to a, b and 0 less than or equal to t less than or equal to fx. So here let me take only for positive reals r plus, so f only takes non-negative values. So this subset is Jordan measurable in R2. In this case, the Jordan measure of EF is exactly the Riemann integral of fx. So I will leave the proof as an exercise because it is essentially a repetition of the proof that was given earlier for the last theorem, which stated that when E is Jordan measurable, if and only if the indicator function is Riemann-Darboux integrable. So I'll just write that you have to carefully repeat the proof given for the statement E subset of AB is Jordan measurable. This was the statement of the theorem that was given before, if and only if the Riemann integral of the indicator function exists. So one has to carefully repeat it because there are some differences between that proof and this proof. Nevertheless, the idea of the proof is entirely the same, and one can replace the we can make the necessary replacements to get the proof for this case as well.